When we think of black holes, we usually imagine objects of unimaginable density, crushing matter into oblivion. But what if I told you that some black holes could have an average density as low as air? How can that be? And if all the mass ends up in a single point, why do black holes get bigger when they swallow more stuff? Let's unravel these black hole paradoxes. First, that density claim. Density is mass divided by volume. For a black hole, the mass is all the matter that collapsed to form it and fell in since. The volume we usually consider is the volume inside its event horizon, the boundary of no return. The radius of this spherical boundary is called the Schwarzschild radius, and it depends directly on the black hole's mass. Here's the surprising math. The radius increases linearly with mass, more mass, bigger radius. But the volume of a sphere increases with the cube of the radius. So as a black hole gets more massive, its volume increases much, much faster than its mass does. Mass divided by a rapidly increasing volume means the average density decreases dramatically as the black hole gets more massive. For a small stellar mass black hole, the average density inside its tiny event horizon is indeed immense, far denser than anything we know. But for a supermassive black hole, like the ones at the centers of galaxies containing millions or billions of times the sun's mass, their event horizons are huge, potentially spanning the size of our solar system. Spread that enormous mass over that colossal volume, and the average density can drop below that of water or even air. It sounds bizarre, but it's a direct consequence of how black hole size scales with mass. Remember, this is the average density within that vast sphere, not the density at the very center. Now, what is a black hole, physically? It's crucial to understand it's not a solid object like a planet or star with a hard surface. The black part isn't a color, it's the absence of light. The event horizon is an invisible boundary in space-time. Any light emitted from inside this boundary, or trying to cross it from within, gets pulled back by the intense gravity. Light from outside that hits the horizon falls in and is lost too. So the region appears black because no light can escape from it to reach our eyes. So where did all the mass go? According to Einstein's general relativity, all the mass that created the black hole and everything that falls in afterwards is crushed down to an infinitely small point at the very center, the singularity, a point of zero volume and, therefore, infinite density. Physicists are confident that infinite density isn't the real picture, that infinity signals that general relativity, our current best theory of gravity, is breaking down. We need a theory of quantum gravity to describe what really happens at that central point. It's likely replaced by something incredibly dense but finite, perhaps a tiny quantum fuzz or something stranger, but not a true mathematical infinity. If the singularity is just a point, or maybe a tiny quantum region, regardless of how much mass it contains, why does the black hole get bigger when more mass falls in? The answer lies in understanding what determines the location of the event horizon. The size of the black hole, its Schwarzschild radius, is given by the formula r equals 2gm divided by c squared. R is the radius, g is the gravitational constant, c is the speed of light, and m is the total mass contained within the horizon. This formula tells us the event horizon's radius is directly proportional to the total mass enclosed. When more mass falls in, it adds to the total m. Even though that mass ends up crushed at the central singularity classically, its gravitational effect contributes to the overall space-time curvature. More total mass means a stronger gravitational field overall, warping space-time more significantly over a larger region. The event horizon is simply the boundary where this space-time warp becomes so intense that the escape velocity reaches the speed of light. As you add mass m, this boundary naturally moves further outwards. Think of it like this. The singularity is the ultimate source of the gravity well, but the location of the point of no return rim depends on the total depth of that well, which is determined by the total mass you've packed into the center. More mass equals a deeper, wider well, pushing the event horizon outwards. So, to sum up, supermassive black holes can have incredibly low average densities because their volume grows faster than their mass. They aren't solid objects but appear black because light is trapped by gravity within the event horizon. Classically, the mass resides at an infinitely dense central singularity, though quantum gravity likely changes this. And crucially, the black hole's size, its event horizon, grows larger with more mass, because the horizon's location depends directly on the total mass warping spacetime inside it. Let me know your thoughts in the comments below. Thanks for watching, and see you in the next one.